This conference will now be recorded.
So very good evening, students. We were discussing space wave communication. So you might be remembering we had already discussed about space wave communication, where we had already discussed what is called space wave communication and how many types of space wave communications are there that we had already classified. Just to recap, the term space wave communication refers to sending, receiving, and processing of information through physical space as the communication medium. The space can be used as communication medium in this type of communication. Okay, so there are three different types of space communication. One is along the ground, which is called ground wave communication. Then directly in the straight line, there is communication through intervening troposphere, which is called space wave or tropospheric wave or surface wave communication. And when we send, so those two we had already discussed, space wave and ground wave. Today we'll discuss another kind, that is the sky wave or ionospheric wave communication. So this is a part of space wave communication or space communication. Okay, so in this sky wave communication, generally what is done is that a radio wave or electromagnetic wave will be sent to the ionosphere, and those radio wave will be reflected by various or different layers of ionosphere back to the earth surface, and at different positions of the earth surface there will be receivers to receive that reflected signal. Okay, so first of all, what is sky wave propagation? Let me write as a definition. What is sky wave communication? Propagation: a radio wave directed towards the sky and and reflected by the ionosphere towards the desired location of the earth is called a sky wave. So in this type of propagation, a radio wave is directed towards the sky and is reflected by the ionosphere towards the desired location of the earth is called sky wave. Okay, so this is not required anyway. So we'll see here. You can see that this is a transmitter which can emit or transmit some signal, and it is actually kind of thrown towards the ionosphere. So these different colors are actually mentioning you that there are different layers of ionosphere according to the number density of ions, etc. There are different layers in the ionosphere. I'll discuss about that also. So the transmitter transmits the signal towards the sky, and there is ionosphere. Okay, and from the different layers of ionosphere, radio waves, different frequencies of the radio waves will be reflected back towards the earth surface, and there will be receiver antenna which will receive. So by using this process, you can actually transmit signal around the globe, okay, around the earth, everywhere in the earth. And see in this, like, what is the frequency range which we can transmit by this Skype wave propagation? It is the range of the signal, frequency range of the signal can be 2 megahertz to 20 megahertz. Okay, beyond 20 megahertz, the signal will penetrate the ionosphere. It will not be reflected back beyond 20 megahertz. Okay. So the region of amplitude modulation band, in this region, see this region of amplitude modulation band is called short wave band. Frequency is too high, so the wavelength will be short. That's why it is called short wave band. Short wave band. Okay, this is short wave band, and these short waves are radiated from certain points of the ionosphere, and after being reflected by ionosphere, it is received by another point. So from here it is transmitted and received here after being reflected by ionosphere. Okay, so this is actually sky wave or ionospheric wave propagation. Now I'll discuss in detail what is ionosphere. You might be having this question, what is ionosphere? Let me tell you this. So what is ionosphere? This is actually telling you, this figure is telling you, suppose this is figure A, this is telling you sky wave propagation, and this is the this is different layers of ionospheric layers, ionospheric layers and sky wave propagation. Okay, So what is ionosphere? It is the outermost region of Earth's atmosphere. Earth atmosphere, you know, there is Earth atmosphere, and outermost outermost layer of outermost layer of Earth atmosphere, Earth's atmosphere, which extends which extends from 65 kilometer to almost around 400 kilometers from of the Earth's surface. Okay, of the Earth's surface. So from Earth's surface, this if this is the whole ionospheric layer, so this height might be uh, up to, see, 65 meter to 400 meter. It is ranging. Okay, 400 meter. Sorry, not meter. This is kilometer. Okay. So ionosphere is the outermost region of the Earth's atmosphere, or outermost layers of the Earth's atmosphere. Now look, since it is very high, at very like at too much altitude, you might be remembering that the pressure will be very low, air pressure, or the atmospheric pressure will be very low at this much height. Okay, 65 to 400 kilometer. In this range, atmospheric pressure will be very low. So when there is very low pressure, let me go to this point. So when there is very low pressure, suppose this is Earth's surface. If it is at sea level the pressure is maximum. So when you go at higher and higher layers, or higher and higher levels, atmospheric pressure will be, suppose this is ionosphere. So here low pressure exists, low pressure. So when there is low pressure, the gas molecules or air molecules over here can be easily ionized. Ionized means what? Electrons can be taken out from the atoms or molecules over there. Atoms, actually atoms. So how is it ionized? Ionized by ultraviolet ray, which is coming from sun, or maybe some higher frequency rays like X-rays. Okay, X-rays, etc., comes from sun. So those radiations will be easily able to ionize the air or the gas atoms over here. So in this region of ionosphere, what you have in the air? You have electrons, positive or negative, some other negative ions. So that's why it is called ionosphere. So these are the constituent elements of this ionosphere. What are there? There will be electrons, there will be positively charged ions, or other negatively charged ions. Okay, but so this is that's why it is called ionosphere. And below this, all the layers are composed of neutral atom. Below this ionosphere are composed of neutral atoms. Only this portion will be easily ionized because of low pressure. And how is it ionized? Getting ionized? It is getting ionized by the ultraviolet ray, which is coming from the sun. So air molecules will absorb that, and then it will be ionized. Same thing with other high frequency rays which are coming from the sun, like X-ray and etc. So those rays or those high frequency radiation will be easily able to ionize the air molecules or the air present in the ionosphere. Excuse me. Okay. So this is how you will have an environment or a region where you have only electrons or positive ions or maybe some other negative ions, etc. Now see, this ionosphere can be subdivided into various levels. According to what? According to the number density of electrons. Okay, according to the number density of electrons or the negative charges or simply charges in that. So there are different layers, like you have D, here it is C actually, C, D, F1, F2, etc. These are, even E also will be there. Yes, C, D, E, F1, F2, etc. These are different layers of ionosphere. Different layers of ionosphere. Now I'll tell you one thing. See, what is C1 layer? Here you have C layer. In this layer you have number density of electrons, something like 10 to the power minus, okay, sorry, 10 to the power 8, 10 to the power plus 8 meter per meter cube. Okay, so this is how, as we go higher and higher, like if I tell you the F2 layer will have 8 into almost 8 into 10 to the power 11 per meter cube. Okay, this is how the number of electrons increases or number of ions increases in the higher level. When the number of ions or electrons increases, then one interesting thing will happen, that is the decrease in the refractive index will happen. That means as you go higher and higher, the air will be rarer compared to the air or the atmosphere near the earth surface. Okay, so yes, so that is the thing. Now what happens, this ionosphere plays an important role in the space. What is that role? Like obviously there are other roles according to geography, but here we are talking about the role of ionosphere in the space communication. So in the space communication it has important role. So you suppose we have high frequency radio waves. High frequency we write in terms of HF. So it has 3 into 30 megahertz. So this range, frequency of this range are 2 to 20 megahertz. This range of radio wave cannot penetrate the ionosphere. Ionosphere. Okay, cannot penetrate the ionosphere. So they are reflected back towards the earth. Okay. So this is the role of this ionosphere. We'll again see, like in the we'll see the details how this reflection happens in ionosphere. So we'll see the mechanism now. So what we have learned here, that there are various levels or various layers of ionosphere, as you see, and these layers are actually composed of different numbers of charge carriers, like charges, like maybe those are electrons, or maybe number of other ions and electron as well. So this number of charges of the ions varies in different layers. Okay, now we can see that very high, ultra high frequency and very high frequency waves will be actually transmitted through the, like those will be actually penetrating through the ionosphere, but the medium again medium frequency radiation, sorry, medium frequency signal will be absorbed by the ionosphere, but high frequency, so these are suppose ultra high frequency UHF, or very high frequency VHF. So these are actually the wave which will be actually transmitted out, penetrating out of the ionosphere, but medium high frequency, okay, those will be reflected back. And actually, here this reflection happens is kind of total internal reflection, total internal reflection. In that method, we'll see that how it is happening. Okay, let me go to this portion again. So how the reflection of radio wave happens from the ionosphere. I'll write in short how ionosphere reflects reflect radio wave. Okay, this is the question now. The answer is that when an electromagnetic wave passes through ionosphere, the electromagnetic radio wave means electromagnetic wave. EM wave actually contains both electric field vector and magnetic field vector. Okay, both will be there. And see, you have in the ionosphere, what you have ions or electrons or positive or some other negative ions, right? So when electric field or electromagnetic wave is just propagating through this region, then electric field vector will be oscillating these ions, right? Because electromagnetic wave has both electric and magnetic field. Electric and magnetic fields are also oscillating. So oscillating frequency, suppose omega. So when the electromagnetic wave passes through this ionosphere, these ions and electrons will be oscillating with the electric field vector. So when they are oscillating, there will be change in the effective dielectric constant. Effective dielectric constant will change. There will be change in the effective dielectric constant, and thereby there will be change in the refractive index. Okay, So I can show you that refractive index, suppose this is n prime, when the electromagnetic wave is propagating, this can be written as dielectric constant, effective dielectric constant into mu 0. Okay, so this can be further simplified in terms of number density of electrons and frequency of the wave and free space permittivity. Okay, so this will be kind of this, like this is refractive index, effective refractive index, effective refractive index, refractive index when EM wave travels through or passes pass through the ionosphere. Okay, so effective refractive index will be changing, and because of that, see what is happening, it is actually passing through this, right? So there will be bending due to refraction, there will be bending of the ray, sorry, the bending of the signal, radio signal or electromagnetic wave signal. So there will be a situation, when critical angle of incidence is achieved, and therefore there will be total internal reflection, and this is how sky wave will be, or the signal will be reflected towards the earth after the critical angle, and there will be reflection from the ionosphere. So the main the gist or the key point over here is how ionosphere reflect radio waves. The key point is that radio wave or electromagnetic wave has electric field vector. So when passing through the ionosphere, there are charged particles. They will be oscillating, and because of that, there will be a change in the refractive index, effective change in the refractive index in the medium of the ionosphere. And when there is a change in the refractive index, signal is penetrating from interface. So this interface has some refractive index, and this has some other. If it is less, n1, and this is n2, so n2 is much greater than n1. So in that case, the refracted ray will be refracted wave will be away from the normal, and thus it starts bending towards the earth surface, and after a critical angle of incidence of this wave, after critical angle, there will be total internal reflection. Okay, so this is how wave propagation happens. Okay, so here there is a table. You can see that the different parts of the ionosphere reflect different ranges of frequencies, and also height. According to the height, we can divide into different parts, like up to 10 kilometer it is called troposphere, very near the earth. Okay, a D part of the ionosphere in this range 65 to 75 kilometer, and beyond that up to 100 kilometer the E level and F level is 170 to 190 kilometer, and 300 kilometer to almost 400 kilometer during daytime. This is actually thermosphere, and here the frequencies which can be used to reflect is here VHF. Then D part can reflect, low frequency, medium frequency will be absorbed, and high frequency also will be absorbed up to some degree, otherwise it will penetrate through that. So this is how you can just read this table, and then you can get some idea about different layers of ionosphere. Okay, so this is how we complete this communication chapter, because we have covered the space of communication, space communication. Now what we'll do, we'll try to pick up few numerical. So before I go to the problem, I'll tell you in this as I said, there will be critical frequency of the sky wave till which the critical frequency of sky wave, that is denoted by FC, till which there will be a reflection. Okay, reflection, and this is given by to the power half. What is this N max? This is the maximum electron density of ionosphere. At different layers there are different, right? So if you know the frequency, sky wave frequency which is suitable for sky wave propagation, because this is the critical frequency beyond which it will penetrate, the wave will penetrate the ionosphere, and below this frequency all the waves will be reflected by the ionosphere. So this is critical frequency of sky wave. Now ground wave has limitations between 0 to 1500 kilohertz, and frequencies above 20 megahertz are carried through satellite communication. Anyway, so what I would like you to do is just remember this critical frequency, and there will be some TV range. TV range has a formula. It is denoted by D. It has formula 2HR. This is the TV range, okay, where R is the radius of the earth and H is the height of the antenna. Okay, so we'll try to pick up few numerical examples. Like say there is a problem, so let me keep this slide as reference. There is a numerical problem. Suppose let me write this problem as Q1. Frequency is higher than 10 megahertz. Question is frequencies higher than 10 megahertz are found not to be reflected by the ionosphere. Ionosphere on a particular day, on a particular day, at a place, okay. So frequencies higher than 10 megahertz is are not received by, that means not received by antenna or receiver. So you have to calculate the maximum electron density of the ionosphere, electron density of the ionosphere. Of the ionosphere. Okay, sorry, this is a statement anyway. So you have to find out the answer for this. So for this we have to use this fc is equal to 9 square root of n max. N max is the maximum number of electron density, okay, or number density, maximum number density of electrons. So we have to find out fc is equal to 9 into maximum density of electrons, okay. So from here you can find out what is this. So let me just square this out. This will be 81 and this will be max. So from here you can see that n max is equal to fc square by 81. So what is fc square? This is 10 megahertz, 10 to 10 to the minus 10 to the power plus 6 whole square by 81. So it will be 100 by 81 into 10 to the power 12. Okay, this is hard. So calculation is actually a little lengthy, but you will be able to find out that the number density will be of the order of 1.23 of the order of 10 to the power 12 per meter cube. So this is the number density, maximum number density. Okay, one more problem will take up. So this is related to TV transmitting antenna, like TV transmission, that is actually surface wave or phase wave. We have already discussed that. Let me tell you that ht, if this is the height of the tower, okay, and r be the radius of the earth, then square root of 2htr will be the range of TV. This is called TV range, television range. Okay, now here you have to remember this thing. We have already written in the previous slide. Let me get you the problem. A TV transmitting antenna, a TV transmitting antenna is 125 meter tall. 125 meter tall. Solar, how much surface area can this transmitting antenna cover? How much? How much surface area Can this transmitting antenna, that means signal will be transmitted. How much service area can this transmitting antenna cover? If receiving antenna is at the ground level, if the receiving antenna is at the ground level, okay, and radius of the earth is given. Radius of the earth is given 6400 kilometer per hour. Sorry, this is kilometer anyway, so this is kilometer. So you have to find out the range. This means how much surface area means you have to find out the range. See, we have written what is range. TV range is D is equal to square root of 2HR, where H is the height of the tower. So we can use this two H and R. H is the height, so here it is 125. R is how much? 6400 into 10 to the power 3 meter. Okay, so if you simplify this, you'll be able to get the area covered. So this will be actually, see, this is the range. This is the range, and area covered you have to do in this way. Area covered, this will be pi into d square, and this would finally the answer I'm writing here, but you can just do the calculation. So this will be up to, this is the maximum range. So area covered will be kilometer square. So this is how, if you remember this, what is the range, formula for range, formula for critical frequency in the space communication, then it is easier to find out or solve numerical problem. So I'll stop it here for today, and by this we have completed this chapter, and in fact we have completed all the chapters of this 12th standard. We have some chapters remaining from the 11th standard. What we'll do for some time, all four classes will be learning about the remaining chapters of the 11th standard, like thermodynamics we have started. So all four classes will go through thermodynamics, then kinetic theory of gas, oscillations. These three chapters will cover quickly by very short time, and then we'll do the revision part. So Wednesday and Sunday classes will, for the time being, learn 11 chapters only. Okay, we were learning 12th part Sunday and Wednesday so far, but all 4 days we will be learning chapters remaining. We'll cover first, and then we'll resume two classes for each, like two lecture for each classes. Okay, so bye for today.